Hey everyone, and welcome to this explainer. Today we are completely demystifying the back-end architecture of global finance. We're going to use an awesome step-by-step architecture design guide created by digital innovation expert Sandeep Kumar to really break down the exact sequence of events that power the SWIFT payment system. Honestly, it's just an incredible piece of engineering, and we're going to see exactly how the whole thing works.
Really think about it. What exactly happens in the mere milliseconds after a bank hits send on a global transfer? When you or, your business transfers money overseas, it kind of feels like magic. Boom, it's sent. But behind that magic is a highly orchestrated, incredibly fast sequence of technological handoffs. So in this explainer, we're going to follow the journey of a single digital transaction. We'll ride right alongside this data packet on a high-speed journey through the system's most critical checkpoints.
Okay, let's dive right into this. Here's our roadmap. We've got 4 main steps. First, the Ingress Layer to capture the message. Second, the Canonicalization Layer to translate it. Third, screening and compliance to secure it. And finally, routing and delivery to send it on its way.
All right, checkpoint 1, the secure gateway. Let's explore the Ingress Layer.
So our digital journey literally kicks off at Bank A. The initiating bank system makes an asynchronous REST API call, specifically a POST request to the /payments endpoint. This one simple line of code is what actually initiates the payment. And because it's asynchronous, Bank A doesn't have to just freeze up and wait around for the entire global journey to finish, right? It just fires off the request and basically lets the SWIFT architecture take the wheel.
The second that REST call is made, the Ingress gateway leaps into action with a few really crucial tasks. First off, it triggers message parsing and validation, basically acting as a secure front door for the incoming message. It has to figure out the exact message type, like is this a traditional MT103 message, or is it perhaps one of the newer PAX.008 formats? And at the exact same time, it's locking things down, ensuring rock-solid encryption and authentication. It's verifying that this message genuinely came from Bank A and hasn't been tampered with along the way. Once it's validated, our payment is ready to move on.
Let's move to and see how this builds in checkpoint 2, the universal translator. Navigating canonicalization.
To get from the Ingress Layer over to the Canonicalization Layer, the system uses an event bus. The Ingress Layer publishes an event called Payment Message Received. You can picture this event bus as a literal baton pass in a high-speed relay race. The Canonicalization Layer is subscribed to this bus, just waiting eagerly. The very moment that event pops up, it grabs the baton and gets to work.
Now you might be wondering, why do we even need a translator? Well, the world of global finance is currently undergoing a massive migration. We have some banks still using legacy standard MT formats, and other banks upgrading to the new, data-rich ISO 2222MX formats. So this layer is absolutely critical for mapping both formats and maintaining backward compatibility during this massive global shift. It makes sure that no matter what format Bank A used, the rest of the system can read it perfectly.
To solve that whole formatting problem, this layer transforms the message into what's called a canonical schema. Think of this as a unified internal model. Basically, it creates a single, understandable language for the rest of the architectural layers. All incoming messages, regardless of their original shape or size, are transformed and stored in this unified model for downstream use. So now, our payment speaks the system's universal language.
Moving right along to checkpoint 3, the high-speed bouncer, screening and compliance.
Triggered by a canonical message-ready event emitted from that previous translation layer, the screening layer immediately takes over. It asynchronously consumes the message and runs the transaction through an absolute gauntlet of security checks. It integrates directly with anti-money laundering, or AML, and sanctions screening engines. It also applies complex anomaly detection rules to spot fraud. This is all to ensure that the money isn't moving to a restricted entity or behaving in a highly suspicious manner.
And this brilliantly illustrates the true power of this architecture. Sub-second. That is the latency we're talking about here. To put that into perspective, it takes you about 300 milliseconds just to blink your eye. Running all of those complex AML, sanctions, and anomaly checks under strict service-level agreements in a fraction of a single second is a staggering engineering feat. It's designed specifically to facilitate modern, real-time payments without compromising even an ounce of global security.
Up next is checkpoint 4, delivery and tracking, the routing layer.
Assuming our payment clears security, a REST API call, post/route payment, brings the results here to our dispatcher phase. This layer is all about the logistics, performing several key actions. Crucially, it attaches a UETR, that's a unique end-to-end transaction reference to the payment. This allows the system to track the payment globally via Swift GPI, kind of like how you would track a package in the mail. It then routes the canonicalized message toward the target bank, all while quietly generating the necessary audit logs and compliance reports in the background. Once all this is prepped, it publishes a payment-ready-for-delivery event.
Which brings us to checkpoint 5, the final confirmation, the end of the journey. Now, what's really interesting about this slide is looking at the entire chronological sequence mapped out. We started with Bank A's post request at 0. By 5 milliseconds, we had the event bus handover. The intense screening checks, done by 100 milliseconds. But look right there at the 150 millisecond mark, the database write. At this stage, the routing and delivery layer performs an asynchronous write operation, a store transaction command, saving the data to the persistence layer. This ensures the transaction is safely recorded in the database right before the final handoff. And that literal handoff happens via one last REST API call, post/deliver payment. This command executes the final delivery of our fully validated, translated, and secured payment data directly into the receiving bank system, which we're calling Bank B. So, the crucial point to take away is right here. The transaction loop officially closes when Bank B responds asynchronously with a payment-acknowledged confirmation event. Bank A initiated it. The Swift architecture processed it through 4 distinct high-speed layers, and Bank B safely received it. The payment is complete.
This brings us to a really fascinating thought to leave you with today. If this invisible plumbing of global finance, managing incredibly complex format translations, multi-layered fraud checks, and global tracking, now happens with sub-second latency, how fast and seamless will the financial architecture of tomorrow be? It's pretty amazing to consider how this foundational step-by-step design might evolve next. I hope this explainer helped you visualize exactly what happens behind the scenes of a global transaction. Keep wondering, keep learning, and thanks so much for exploring this with me.